if you do writes on all nodes, at which point does it kind of stop being beneficial? And from the benchmarks, I've seen it somewhere between 5 and 8 nodes, depending on what type of transactions you have, where you don't gain anything anymore by adding more nodes. But typically, I mean, we have a lot of customers using Galera, and 80% or 90% are using 3 nodes. They don't use any more because that's already good enough. But you can add nodes and you get some benefit from that. And same as with replication, though, you need some kind of load balancer because well, to hide the cluster nodes from your application, so the application doesn't have to be aware of which nodes are there, which nodes are up to date, and what if a node crashes and so forth. So you need some kind of load balancer for it. Any questions about Galera? Well, this is going well. Everyone is no one has any questions. I must be doing a really good job. So if you look at load balancers, then for both Galera and replication, there's, I mean, the main reason, as I said, for load balancer is so that the application does not have to include any kind of logic for the cluster. There's a couple of examples here. HA proxy is an open source one. Galera load balancer is specific to Galera. The JDBC client, or it should actually be called connector. The JDBC connector actually has built-in load balancing, very basic load balancing, but still, you can basically give it a list of servers, and it assumes the first server is a master, the others are slaves, and it will distribute your traffic according to that. Then you can use MySQL Fabric, which also allows sharding, which is a bit more complicated. And then we have our own MaxScale, which I will just mention in a few slides here. So a load balancer in general needs to be able to obviously monitor your nodes, so that if a node goes down, the load balancer doesn't send queries to it. And some proxies that are generic, depending on your what type of technology you're using behind, a generic load balancer might not be enough. For example, HA proxy, when we started using it, we used it for Galera clusters, but the problem was that it was only checking whether a MySQL server was up or down. And in a Galera cluster, a MySQL or MariaDB server can be up, but not synchronized. So you shouldn't send anything. I mean, the server will refuse any kind of queries, so they will fail anyway. But you waste a lot of, you get a lot of aborted transactions just because you send queries to a server that's actually not there. So you need to have monitoring that's actually applied to your underlying technology, right? So you need to be aware of, okay, how does Galera work? When is a Galera node synchronized? And so forth. And if you use replication, you typically want to be aware of the slave lag as well, because you want, if a slave is lagging a day, you probably don't want to read from that slave. I mean, maybe you do, but depending on your application, you might have requirements on which slaves can be read from and which cannot due to things like this. And I mean, those are some of the things we've built into MaxScale. We obviously know MariaDB quite a bit, so we have this knowledge in-house. So I don't want to talk too much about MaxScale, but just a few use cases. So to give an idea, so MaxScale also has a read-write split router built in, which means that if you use standard replication, you have a master and you have slaves. MaxScale allows you to just connect to MaxScale, and based on the queries coming, it will decide whether to send this to the master or to the slaves. Right. So it's a read-write, and which is fairly useful. Well, if again, depending a bit on your transactions. Obviously, if you have large transactions that have both writes and reads, they will all go to the master because it won't be able to tell in advance whether this is going to be a read or a write. So it will only work in some cases. It won't work. Well, it won't work in all cases. And basically, the MaxScale proxy, it looks like a MySQL server, MariaDB server. So your application thinks, or your clients, they think they're connecting to to MariaDB or MySQL, but they're actually connecting to MaxScale, and MaxScale then decides, it gets the queries from the application, and then it decides, okay, what do I do with these queries? In this case, using the read-write split router, it will check, okay, is this a read query, a write query, or a query where I don't really know what it is? And for write queries and the I don't know ones, it will send them to the master, and for the rest, it will do a load balancing on the slaves. And here, MaxScale also has the capability. You can give it rules. Okay, if a slave lags more than this, the slave should not be used, and things like that. Then you can say, okay, I want to load balance based on connections on the slaves or something like that. So you can choose that. MaxScale can also be used with Galera because we have a built-in Galera monitor. And again, you can actually use the read-write split router as well, but you can also allow MaxScale to just do round robin across the Galera node, which is typically the best way from a load balancing perspective. In which case, basically, you connect to MaxScale. It looks like one MariaDB server, but MaxScale will actually redirect this to one of the active servers in the Galera cluster. Again, one of the main benefits is that MaxScale takes care of monitoring whether all the nodes are there. So your application doesn't have to worry about, hey, do I have 3 nodes? Do I have 4 nodes? Which one is running? And so forth, because MaxScale takes care of it, right? So the transparency is a huge benefit. And you can use the read, even if you're using Galera, you can actually use the read-write split router with MaxScale as well. Now, what would the benefit be of doing that instead of the previous one? Exactly. The answer is that way you don't have to worry about potential conflicts. So you can set up Galera in a normal cluster, but you send all your writes to one node. This way, it perhaps doesn't scale writes as much, but you will never have any conflicts because all writes are going to one node, so there cannot be any conflict. So you never have aborted transactions due to conflicts. So how does it handle a local deadlock conflict? Well, the same way as InnoDB does. So it's all InnoDB, and InnoDB has a deadlock conflict detector built in. So if there's a deadlock in one server, InnoDB will detect it and it will abort the latest statement, basically. And it's the same way. So it's all based on InnoDB because if all the writes go to one machine, everything is local. So it's done the same way as if you only had one machine. So that's kind of the benefit of using something like this. And again, I mean, in Galera, there is no real master, so it doesn't really matter which server is the master. And if that server fails, some other one will become the master. And this is something that actually MaxScale will do. There's no master definition inside Galera. It's purely from the proxy perspective, the master definition. Oh, you mean can you decide with have a preference order for the write? I actually don't know. Do you know, Daniel? No, I actually don't know if you can do that. My guess is yes, but I'm not 100% sure. And it shouldn't be very hard to code if it's not there yet. So yeah. No, I mean, so even if it doesn't have that, it will automatically fail over to another node. It's just that can you have an order of preference or not? But even if you can't, basically we'll choose one node. If that node fails, it will just use the next one. So that works for sure. And in general, with a Galera cluster, because all machines will do the same thing, you want your nodes to basically have exactly the same hardware anyway. The cluster will be as fast as your slowest machine, so there's no point having one that's faster than the others in a Galera cluster. In replication, you can do things like we had the fan-in slave and things like that, but where it might make sense to have one machine faster than others. But in Galera, they're all equal, so they should have the same hardware. Any other questions about Galera? or MaxScale for that matter. All right, then we get to the most fun part, which is sharding. So, I mean, what is sharding? It basically means that you're splitting up something in different pieces and they're independent. In this case, we're splitting up the database in some way across multiple instances. And now, you know, there's different ways of doing sharding. You can do schema-based sharding, which basically means that you have different schemas on different machines. So it's very much a logical division. You can have some parts of your application and in this server or this server cluster, and then you have other parts in another server. And it can be something that's done on the application level, so that the application is actually aware of the split and it knows that, okay, if I'm doing like a purchase, I should go to these databases. If I am doing some kind of analytics, I go to these databases. So it's a sharding that's very much built into your application logic. But you can also have it in a lower level. You can, well, actually MaxScale has a built-in schema-based sharding. So you can actually use MaxScale for having separation on the schema level. So everyone connects to MaxScale, and the application is not aware that actually if you query that schema, it will go to a different server than if you query that schema. It's done by the proxy. So the application is not aware of the sharding. But then sharding can also be done on a lower level, because this, of course, only works if you have multiple schemas and you have a fairly even distribution between load between the schemas. But if you have one table where you have a huge load, that doesn't help. The only way to get past that is to use key-based sharding. So basically, you split your table into different pieces based on primary key values, and then these different pieces will be on different machines. Right. And how you implement sharding? So you can do it in the application, independently of whether it's key-based or schema-based sharding. You can do it in the application level. Again, the problem is that your application has to be aware of this, and if you make changes, you have to change the application and so forth. You can do it through the connectors, for example, using MySQL Fabric. You can do it through the proxy, or there are storage engines that allow sharding as well, or have built-in sharding. For example, NDB, which is MySQL cluster, has built-in sharding, so it's automatically sharding. There's a storage engine called Scalability, which has built-in sharding. And then there's a storage engine called Spider, which basically is sharding. I'm going to talk a bit about Spider here later on, just because it's so simple. So, well, I don't have any advantages with sharding here. I only have disadvantages, but the advantages... The advantage with sharding is, of course, well, you need to do it because you can't, and the resources of one machine are not enough, right? So you have to split up somehow. And by using multiple machines, you can then do certain things faster. The problem is that because you split your data, you will have an increased complexity of SQL. Well, especially if you have key-based sharding, right? Because if using key-based sharding, this means that the speed or your performance or your operations will be handled differently. How do you do a full table scan from a sharded table? How do you do a normal index scan from a sharded table and things like that? Everything becomes more complex. And depending on where you shard, you might not be able to do it in one statement. You might have to do multiple statements to get the same result as you would earlier get with one statement, depending on where you shard. It's obviously more complex to manage because you have multiple pieces. So for example, if you have one server, you need some HA. You set up an HA solution for that server. Well, if you have 10, any one of these 10 pieces failing, and your cluster is out. So you have to set that up. So failover becomes more complex. What if one piece fails and it fails over? Should the others be available during the failover? Should they not? And things like that. So there's more things to think about for that. And same with backups. Again, you have 10 machines. You take a backup. Well, how do you synchronize the backup? Taking a backup from one MySQL MariaDB server is easy. There's lots of tools for taking one backup and having it synchronized. But doing it across 10 is not so easy anymore, because how do you synchronize the queries so that they're consistent across all the 10 shards. So you have to think about that as well. So there's a lot of disadvantages with sharding, but if you have to do it, you have to do it, right? So I already mentioned this. Basically, you can shard on different levels. So if you shard on the application or in the connector, it basically means that the application will directly connect to the different machines or different shards. And here, the application has to be aware of how you shard or something. And if you do it on a proxy level, then the application doesn't have to be aware of the sharding, which makes it a lot easier for the application layer. And then you can do it through a storage engine, which basically means, well, you don't even need a proxy in that case because you connect to a database server and the sharding is happening underneath the hood in the storage layer or in some other layer. So as an example of sharding, I'm going to talk a bit about Spider, which is has anyone heard about Spider? Has anyone used Spider? No. Okay, so Spider is a storage engine in MariaDB. So it looks like it stores data, but it doesn't actually store data. It's actually the basic principle of Spider is extremely simple. Basically, you create a Spider table with a partitioning scheme. Who has used partitioning in MySQL or MariaDB? Okay, half. So basically, in MySQL or MariaDB, you can say partition by, and you can choose list partitioning. So you define range. You define a list of values, and they will go into one, and another list of values they will go into second. You can do range partitioning, where you have ranges of values. For example, dates. You can put all the rows with a specific date range to go into one partition and another date range and so forth. So you define ranges, and then you have hash partitioning and key partitioning, which is basically saying that, well, you don't really care how it's divided as long as it's divided, right? So what Spider does is it basically uses your partitioning scheme, but instead of with normal partitioning, basically you partition your table, but all the tables are still locally. What Spider does is that it actually, instead of storing the data locally, it creates remote connections to other MariaDB servers. So you don't actually store anything locally, you store it on remote servers. So basically it does sharding for you, in a sense. So that's kind of the really basic idea behind Spider, but it becomes more complex because, of course, it has to handle transactions. Now, this is easy because we support XA transactions, so we can have distributed transactions through XA, and that's also how Spider does it. So when you have a transaction, it will create a transaction on all of the nodes. Transaction that spans all the nodes, and when a transaction is done, it will be committed on all the nodes. And we have XA transactions that supports this, so it's kind of built into MariaDB and MySQL. So if you look at a Spider table, basically no data is stored locally. Instead, it's stored on the shards. And you can, because the shards are MariaDB servers, this means that you can access the data through the Spider server or directly through these remote servers or sharded servers. And this is also easy for, this is also a good example for highlighting kind of the potential problems with key-based sharding. So typically you have one or two tables that are huge that you need to shard, and the other tables might be smaller, so you can actually maintain them as non-Spider tables, right? So the small tables are on the Spider server, right? Now you want to do a key value lookup. You have a primary key value, and you want to get it from this table. This, you go to the Spider node. The Spider node, through the partitioning, knows where to get it from, and you get it. It's fast. It's quick. It will typically be a lot faster than having one machine with all the data, because on the smaller machines, on the shards, everything will fit in memory, so it will be a faster operation, right? So key value lookups are great for key-based sharding. Now the problem is, what if you have a where clause that spans a range of values? And that's where key-based sharding is not so great anymore, because there is no way of knowing which shard will have the data. You basically have to send this query to all of the shards, and all the shards send their data back, and then you create your result set and you give it back. Okay, that's still okay, but what about joins? So you want to join your sharded table with a non-sharded table. Now this is where we have a problem. So traditionally in MySQL and MariaDB, there used to be only one way to do joins, called nested loop joins, which is basically nested for loops, right? So you take the outer table, start with the first row, then you go to the next table, and then you go back and do it again. So you go through like a for loop, like nested for loops, finding the rows for the join. And this works fine if everything is in local memory. But if one of the tables is a spider table, every time you fetch a row, you have to go out on the network, right? So if you do a nested loop join where you have to get a row like 500 times, you basically have to go on the network 500 times, and then 1,000,000 times you basically kill your query because of latency, right? So doing joins with sharded tables is not great. This is, many of the NoSQL solutions, they shard everything, but you typically can't do joins, and this is the reason, because it's actually a hard problem. You can't really, there's no good solution for it. And Spider actually has, I mean, we have added some optimizations in it. We have a batch key joins. You can do batch key access. Instead of doing one row at a time, you do a range of rows at a time, which makes it a bit faster, so you don't have to take every single row one at a time, but you take a batch of rows. But Spider itself actually offers functionalities for getting around this. So, for example, if you have a smaller table that you want to join with, and you also store the same smaller table on every single shard, Spider allows you to basically create the join, do the joins locally, and send the result sets. So basically, the join operation is done on the shards instead of on the Spider node, and that way you only have to do one network hop. The operation is done. The operation is actually spread out. Everyone does the join operation, and then the only thing the Spider node does is gathers together the result set. So that way, even joins can be actually quite fast with Spider. But this is not something that you have to use specific functions for this. It's not built in. So if you just use the normal MariaDB, I mean, if you just write a query, the optimizer is not aware of the optimizer is not Spider aware, so it won't be able to do this for you. It doesn't know that you might have local tables on the other nodes and so forth, but Spider has built-in functionality for it. All right, some other cool things with Spider is that so the linked table can have any engine, right? So the remote tables, so you create your shards, and the Spider table uses Spider as the engine, but on the shards, you can actually use any engine, and you can actually use different engines. So you can have InnoDB for some and MySQL for some. Okay, there might be a good reason for that. You can also use partitioning on the remote tables, and the remote servers are not Spider aware. They don't actually know that they're just a shard. They're just a server, and they happen to be accessed by Spider. And you can have multiple Spider nodes for the same table. So if you look at this image here, I could basically have another Spider node here. It just has to have the same definition of the tables connected to the same nodes. So basically, the main use case is high availability. If the Spider nodes go down, suddenly you can't access anything. But if you have two of them, it doesn't matter which way you go, because they don't actually store much data. They don't store anything for the Spider tables. They might store something for other tables if you have non-sharded tables. So here's an example of how you do it. So on the Spider node, you create a table with engine Spider, and then you basically define how to connect to the other tables. And here, my example is not that great actually, because I only have one. I only have one node here. I should have a connection to multiple nodes, so I must have missed something when I put this together. But basically, you would have a yeah. But actually, okay, I have two examples. Sorry, I confused myself. I have two examples here. This is a much better example. So here I have a spider example with sharding. So here I create a table on the spider node. I have a partitioning scheme, and then for each partition, I say, okay, where is this shard located? Because it won't be local. So basically, for each partition, it gives which server to connect to, right? So here we have a table with 3 partitions, and then we created the spider node. We obviously have to create the tables on all of the shard nodes, and then we can insert or select queries from the spider node. And well, here I inserted 3 nodes, and then if you look on each node, you will see that each node will only have one of the rows on this table. There. So a few words about performance with Spider. So reading is generally faster, except for joins where it can be slower because of the problems I just mentioned. And writing, which is typically one of the main reasons for using Spider, is insert speed is generally a lot faster because you only insert to one of the shards. So you can do lots of inserts in parallel, right? Because if you have 10 nodes, well, you can write, or 10 shards, you can write on all 10 machines at the same time. So you kind of gain huge increase in write speed. That's typically the main reason. Typically, the main reason for using Spider is this. And here's just a summary of what I went through here. So replication is good for read scaling, and Galera is mainly for read scaling, but gives HA as well, and also the fact that the nodes are synchronized, which means that you don't have to worry about slave lag. And then sharding, which I would say should only be used if you really have to, but depending on how you use it. So I mean, obviously, I mentioned Spider here because it's easy and I actually like Spider, but also because you know, it's an interesting example because it's on the database server. But there are sharding proxies out there that goes in front of your database servers, as I said. So like MaxScale can do schema-based sharding, but you can get key-based sharding as well. There's like scale-based and some others as well. All right. Any questions?
On the schema-based sharding, when you're on the MaxScale.
Mm-hmm.
Okay, the question I have there. So when you're scaling that out, can you does it automatically take care of all those different shards as it's pushing it down? Like, let's say if I'm doing a write to a table that's coming down through, it's going through my shards, and then let's say I have one of those nodes goes down there. How long does it, like, is it going to propagate back up? I guess is my question. And like say, hey, there's a problem here.
Yeah. So
like, I'm just interested on that part of that the proxy software.
Okay. So I mean, MaxScale, because it's aware of, it depends on what you, so typically when you do the sharding like this, you have to have some kind of HA for each shard, right? And MaxScale, of course, is aware of Galera and replication. So if you're using Galera or standard replication for each shard, then there's no issue, because it's same way we saw it Galera works with if you only have one shard, like you only have one master slave or you only have one Galera cluster, MaxScale works. So with the schema-based sharding, it's basically the same thing, except that you have multiple of these. So it will monitor all of the machines. If the master fails, it will start using the new master and so forth. So basically, it will work out of the box. But you have to set it, but it doesn't create HA for you. So you have to still set up the HA. You have to make sure that you are using Galera for each shard, or I mean, whatever you are using. So yeah. Yeah. All right. So the question was, how does MaxScale know where schemas are? So basically, you define that. So MaxScale, you basically define how to shard the different schemas. Right. So if in schema-based sharding, the question was, how do you deal with like if you have different loads for different schemas? So, I mean, that's kind of where schema-based sharding doesn't work so well anymore. Is when if you have one schema or one table that's getting all the traffic. So I mean, your example, for example, if you have like one schema per customer, some customers have much more traffic than others, then you can put multiple schemas in the same cluster and then separate out the one that has the most traffic, and that's its own cluster, and then you have 10 on the other cluster or something. So that would be a way to get around it, but it might not work. It depends on how different the loads are, right? Right. I'm not sure. Daniel, do you know? Can you send me the question by email, and I'll make sure to get an answer, because I'm not sure actually. I actually haven't used the schema-based sharding myself. I think we're running out of time, so feel free to send me if you have any questions. Well, grab me after this or send me an email. Thanks.
Your customers rely on your website or application. If it's slow or non-responsive, it infuriates your users and costs you money. Keeping your business-critical systems humming along requires insight into what they're doing. Your system metrics tell stories that can reveal performance bottlenecks, resource limitations, and other problems. But how do you keep an eye on all of your system's performance metrics in real time and record this data for later analysis? Enter Longview, the new way to see what's really going on under the hood. The Longview dashboard lets you visualize the status of all your systems, providing you with a bird's-eye view of your entire fleet. You can sort by CPU, memory, swap, processes load, and network usage. Click a specific system to access its individual dashboard, then click and drag to zoom in on choke points and get more detail. Comprehensive network data, including inbound and outbound traffic, is available on the Network tab, and disk writes and free space on the Disks tab, while the Process Explorer displays usage statistics for individual processes. The System Info tab shows listening services, active connections, and available updates. Adding Longview to a system is easy. Just click the button, copy the one-line installation command, then run the command on your Linux system to complete the process. The agent will begin collecting data and sending it to Longview. Then the graphs start rolling. Use Longview to gain visibility into your servers, so when your website or app heats up, it stays up.
Citrix Zen Server gives you everything you need to integrate, manage, and automate a virtual data center, all on an enterprise-class, cloud-proven virtual platform, and at a third of the cost of other solutions. But why even bother with virtualizing your server infrastructure in the first place? Well, let's say you have a traditional one server to one application architecture, but you're running out of resources and performance is suffering. Once you order new server hardware, you'll wait for delivery, configure it, install your business application, stage and test the server, and finally, add it to your production farm. If you've been through this process before, you know it can take weeks or even months. You also know it's a manually intensive process that will burden your team every time you outgrow your current setup. With a virtual server solution, you could accomplish all of that in less than half a day. Server virtualization software separates the OS and application from the underlying server hardware. And with multiple virtual machines on a single server, you can use each of them to run different OSs and applications. This makes it possible to move your virtual machines from one piece of hardware to another whenever you want, to maximize utilization, simplify maintenance, or recover from a hardware failure, and without slowing down your applications or users. Clearly, server virtualization provides big benefits, and Citrix Zen Server provides even more. Since it's built on an open platform, Zen Server plays well with your existing hardware, storage systems, and IT management software, as well as with the industry's leading cloud service providers. Best of all, you can get started by downloading a fully functional, production-ready version of Zen Server for free. After a 10-minute installation process, you'll see how easy it is to start virtualizing your workloads and automating your IT management processes. And when you're ready for a richer set of management tools, just upgrade to one of the premium editions of Zen Server. So whether you're interested in virtualizing servers for the first time, expanding your server virtualization footprint, or moving server workloads to the cloud, download and install Zen Server today and see how it can help you simplify your IT environment. Citrix Zen Server. Do more. Don't spend more.